spent so much time on this stupid dog. So this was the one that really got us. So you take the dog, put him on a step like this, drop him, okay? It would bounce twice and then slide, right? So the friction model that made that happen was just ridiculous. But we got it right, eventually. It turns out there was some interplay between the springs and the legs and the ground reaction forces. But we have a very accurate dynamic model, okay? And now we formulate the problem. This is just like the bug trap. We're just going to say, okay, your initial conditions are here. The dynamics are given this model. I want you to get here, okay? Go ahead and solve it, right? And it's a really, really hard problem. There's all these options of getting stuck here, but we can, in a few minutes of computation with these random algorithms and the dynamics, modifications for them, we can plan these pretty aggressive trajectories over the obstacles. And once we have a trajectory, we always know how to stabilize them. We've gotten a little better at stabilizing trajectories recently. We always use, well, that was the other guy's controller, I should have said, but we use local linear controllers around trajectories to stabilize these things. It turns out it makes a big difference if you use the same construction of a transversal coordinates around a limit cycle, so you're not stabilizing in time. So this is an idea that came from Sharia, and that makes a big difference to stabilize trajectories in the transverse coordinates. And we can make, so the blue was the actual trajectory, the red was the other guy's controller, the green is our controller, but also subjected to adversarial disturbances. Every time his foot hits the ground, we give him an impulse like this, like, "Ha, you probably didn't know where the ground was. Just for kicks, I'm going to throw you up and you can recover very robustly." All right, so here's how we put it all together. Okay, so I've got my pendulum. I know how to make trajectories now. I just showed you we got good tools even for little dog type robots for making trajectories, and we know how to make funnels. Okay, so here's how it goes all together. So I told you we can make the funnels around the trajectories. You should really think about these as, I guess I already said the word funnels, so you should really think about these not just as regions. Lyapunov functions have a beautiful image as funnels, okay? So think of it, that function b of x, which is always going downhill, as a funnel in state space, which takes initial conditions here and brings them down to 2, right? Takes initial conditions here, brings them down to 2. So if I have a funnel that I've computed, which takes initial conditions here and brings them to the goal, and if I can design another funnel that goes around this trajectory, subject to the constraints that this funnel, the output ends in the inlet of this funnel, then I can start putting everything together. Let's just think of that as another funnel. Then I can start putting all these things together. I can start with the initial swing up trajectory that gets me to the goal, and now I'll do a randomized algorithm to just try to make a better controller. Okay, so I'm going to pick a point at random. When I pick a point at random, if it was already in somebody's funnel, I can just throw that point away. I don't need that. That one's already taken care of. If it was outside, I'm going to design a trajectory now that tries to get back